What if the universe's edge isn't the final boundary, but the starting point of something far more enigmatic? A space telescope has recently looked deeper than any instrument before it, detecting light from the earliest moments of time and uncovering galaxies far older than our current models had anticipated. Physicist Michio Kaku describes it as a glimpse into the very act of creation. And what this telescope discovered isn't just ancient tits bizarre. It's forcing us to revise our cosmic timeline and consider powers we haven't yet grasped. Could this be pointing toward primordial black holes or perhaps hints of other universes entirely? One thing is now certain. What we once thought of as the edge of the universe is now closer, more defined, and within our reach. Our journey begins by focusing this observatory on the limit of what we can see, roughly 46.5 billion light-years away. This edge isn't a solid barrier. It's defined by how far light has traveled since the Big Bang. No telescope can view. Infinite space, we can only observe what light has had time to deliver. Using advanced infrared detection, this telescope sees light that has crossed a growing universe for more than 13 billion years. Immediately, it surpassed earlier records. Faint glimmers that once appeared as smudges through older instruments now resolve into 44 distinct galaxies. Some emitting light from redshifts above, Z approximately 13. That means their light was released when the universe was under 300 million years old. As Kaku explained, we're not just seeing into the past, we're witnessing the universe's first galaxies forming. And that isn't poetic flourish, it's literal. This isn't just a faint glow, it's ancient starlight. The fossilized traces of the very first stars turning on. These early galaxies, cosmic nurseries, contain critical clues to the infancy of our universe, and now we can study them directly. The telescope doesn't merely detect their presence. It separates each galaxy from its neighbors, capturing detailed snapshots of the universe's early neighborhoods. These aren't novelty images. They're fragments of history, inscribed in ancient light. Each photon helps us visualize the initial seeds that eventually blossomed into galaxies like our own. As Kaku notes, we're not just seeing distant light, we're watching the very foundation of cosmic structure unfold. This breakthrough is rewriting everything next. We dive into how these unprecedented redshift observations are reshaping our understanding of cosmic history and star formation. The universe started its evolution both earlier and faster than we previously believed, by setting new redshift benchmarks. This telescope has changed the game. It uncovered galaxies at redshifts greater than Z approximately 13, meaning they existed when the cosmos was younger than 300 million years. Scientists once expected to find only a few of these ancient galaxies, but nearly 44 new candidates have emerged, all appearing dormant since the universe's dawn. These discoveries suggest that our prior cosmic timelines were far too cautious, too. Put it in perspective, it's like discovering fully built cathedrals in what was thought to be a primitive village, or towering skyscrapers in a town barely formed. As Kaku put it, these galaxies aren't blurry flickers. They're the universe's first urban centers. Detailed, organized, and unexpectedly mature. This telescope hasn't just revealed more galaxies, it has captured sharper details, greater mass, brightness, and star formation rates than our current models predicted. Theories based on cosmic inflation and dark matter assumed a slower buildup. But what we see instead is a universe that raced ahead from the start. Kaku warns that these results may force a rewrite of our cosmological theories. These revelations are urgent. If galaxies emerged faster and more efficiently than expected, our understanding of dark matter behavior, cooling gas, and star-making processes needs reassessment. That's no small correction. It may point to an entire early period of cosmic acceleration that we're only beginning to detect. And those galaxies aren't just early, they're structurally complex. Let's now examine how deep field images are exposing internal components, disks, clumps, and filament skis, to understanding how galaxies first formed in these microscopic glimpses of the early cosmos. We don't just see dots, we see organization. Clumps of matter, swirling disks, and delicate filaments emerged when the universe was just 200 to 400 million years old. Even then, material wasn't scattered randomly. was shaping itself into galactic structures. Inside these primordial galaxies, we see luminous regions, stellar nurseries, flickering like early solar systems in the making. Kaku describes them as the first steps toward galaxies like the Milky Way. These glowing spots are embryonic clusters of stars, guiding us through the early evolution of galactic structure. Such observations are transformative. They allow scientists to measure how early galaxies spun, grew, and interacted with dark matter. We can estimate their mass, identify the movement of gases, and track how star birth affected their environments. Processes once believed to occur much later in the universe's timeline. Technically, the detail is stunning. These aren't just photos of distant objects, they're blueprints of cosmic architecture, Kaku said. They're glimpses of the cosmic framework from which everything, including our galaxy, developed. But there's a bigger issue. These galaxies are forming too fast, too large, and too bright to fit inside our standard models. That's the next frontier, confronting the challenges facing modern cosmology. This telescope hasn't just opened a window into the past, it has flung the door wide open. What we're finding is both exhilarating and problematic. Many of the early, luminous galaxies discovered appear too massive and too complex to fit comfortably within our long-standing cosmological frameworks, such as the lambda-cold dark matter CDM model. This foundational theory predicts how dark energy and dark matter shape the universe. The cracks are beginning to show. The galaxies spotted at extreme redshift seem to have formed stars much faster and more efficiently than expected. Standard theories suggest matter needed time to cool, condense, and ignite. What we're seeing challenges that assumption. Kaku puts it bluntly. It's as if the universe skipped adolescence. These galaxies matured in a cosmic blink, suggesting the involvement of new, unknown physics. If galaxy formation occurred faster than assumed, our views on early dark matter structures, cosmic feedback, and early gas temperatures must be reevaluated. Some researchers are proposing tweaks to inflation theory. Others are questioning whether dark matter behaves as we thought. This doesn't mean the CDM model is completely broken, but it might be incomplete, like a puzzle with a few crucial pieces. Missing this is a defining moment in theoretical physics. As Kaku reminds us, it's not that our theories are wrong, it's that the universe is more creative than we imagined. And when imagination meets evidence, discovery is inevitable. So where does this lead? Toward possibilities even more exotic-like. The hunt for black holes formed not from stars, but from the Big Bang itself. Among the telescope's strangest findings are subtle excesses of infrared light. Faint glows that don't align with young stars or known galaxies. These may be signs of something much older. Primordial black holes formed during the universe's earliest moments. Not from dying stars, but directly from the chaotic energy of cosmic inflation. If these black holes are real, they may have seeded the growth of galaxies themselves. That would invert our usual understanding. Instead of galaxies forming black holes may have formed galaxies. Kaku suggests that if true, this could redefine what sparked the cosmic dawn. These ancient black holes might have pulled in material and triggered early bursts of star formation, helping shape the very structure of the cosmos. And they may also be tied to dark matter, the invisible mass that makes up most of the universe, but doesn't emit light. If these early black holes turn out to be dark matter, or at least part of it, it could solve one of physics' deepest puzzles with a single explanation. We don't yet have proof. But the signs, gravitational lensing, spectral irregularities, and unexpected brightness are piling up. As Kaku warns, we may have mistaken shadows for stars. To understand how stars first emerged from the darkness, we now move to a pivotal era in cosmic history, reionization. Once the universe was truly dark, not symbolically, but physically filled with a thick hydrogen fog. After the Big Bang's initial flash, the cosmos entered a long dark age without stars, where light barely traveled. Then came a sudden transformation. Stars ignited, galaxies emerged. The lights switched on. This phase is known as reionization. And now, thanks to new observations, we can see it happening.